Today we'll be analysing the John Nillard Scientia building, which was completed in 2000 and designed by Francis Jones Morphine Thorpe. The building is used as a ceremonial hall and function centre and has received major architectural awards in Australia. Its design is made up of three main elements: a sandstone base, aluminium-clad upper levels, and a central timber structure. In this presentation, we'll examine the key materials used, assess their performance and sustainability, and then propose more sustainable alternatives.
The John Nyland Scientia building uses a clear set of materials across its main components, starting with the structural materials. Precast concrete profiles woven through the sandstone podium, forming horizontal courses, louvres, and balustrades. Laminated Oregon timber columns, 12 in total, providing the main vertical support for the foyer roof. The non-structural materials are sandstone cladding to the podium, aluminium paddles to the upper volumes, including integrated louvres, beech and silky oak timber panels lining the interior walls, cast plaster ceilings forming the ribbon-like hall surface, and glass and jarrah timber used in the foyer tree supported by a steel frame. Now looking at the properties and function of each material. Precast concrete has high compressive strength as it is factory controlled. Its function is self-supporting louvres and balustrades. Laminated Oregon timber is engineered for higher strength compared to solid timber, and it functions as the primary vertical support for the roof. Sandstone has high compressive strength and a high thermal mass. It grounds the building and provides passive thermal regulation. Aluminium is lightweight and is 1/3 the density of steel. It is corrosion resistant and it weatherproofs the upper volumes and forms solar filtering louvres. Beech and silky oak panels are hardwood with acoustic absorption and diffusion properties. It is used for interior wall linings to reduce echo and reverberation. Cast plaster is smooth, fire-resistant, moldable, and acoustically reflective. It forms the ribbon-like ceiling and contributes to acoustic performance. Glass is transparent and weather-resistant. It is used in the foyer tree canopy to admit daylight while providing enclosure. Jarrah timber is dense, durable hardwood with a warm reddish color. It's used to form the branching tree foyer structure. Now looking at the selection criteria behind these material choices. For structural performance, laminated Oregon timber was selected for its high strength to weight ratio, enabling slender columns without bulky cross sections. Precast concrete was chosen for its ability to span as a self-supporting element, which is ideal for louvres and balustrades. For site and campus context, the sandstone podium references UNSW's historic sandstone buildings and the natural geology of the campus hill, while the aluminium cladding expresses the modern, contemporary identity of the university. For environmental factors, aluminium louvres on the east and west facades filter sunlight, reducing glare and heat gain. Sandstone's thermal mass moderates temperature fluctuations, reducing heat and cooling loads. For aesthetic features, as the materials in the building transition from sandstone to concrete and finally to aluminium, the building shifts from a natural to engineered materials. The jarrah foyer tree and warm timber finishes create a feeling of openness and shelter, mimicking a natural tree.
Precast concrete structural material life cycle sustainability assessment. This LCSA assesses the sustainability of precast concrete used in the Scientia building across its full life cycle. The aim is to understand how the material performs environmentally, economically, and socially. This helps determine whether it's a suitable long-term material choice. It uses a cradle-to-grave approach, evaluating impacts from raw material extraction through to end of life. This includes environmental, economic, and social factors at each stage. By doing this, we get a complete picture of the material's overall sustainability. The material goes through several stages, including raw material extraction, manufacturing, transport, construction, use, and disposal. Each stage contributes differently to its overall impact. Understanding these stages helps identify where the biggest impact occurs. The biggest issue is its high CO2 emissions from cement production, along with large energy consumption and resource depletion. These impacts mainly occur during the manufacturing stage. This makes precast concrete one of the more environmentally intensive construction materials. However, precast concrete also provides benefits over its life cycle. Its thermal mass helps regulate indoor temperature, improving energy efficiency. It also reduces construction waste and can be recycled at the end of its life. Economically, precast concrete allows for faster construction and reduces on-site labor costs. It is also very durable, meaning lower maintenance over its lifetime. Socially, off-site manufacturing improves safety, although some impacts like dust and noise still exist. Overall, precast concrete performs well in terms of strength, durability, and cost efficiency. However, its high embodied carbon is a major limitation. To improve sustainability, alternatives like low carbon concrete and more efficient materials should be used or considered.
Aluminium panels are used as louvre cladding to control sunlight, improve comfort, and create a transparent facade. This assessment evaluates aluminium panels across their full life cycle to determine their sustainability performance. Aluminium is produced from bauxite through energy-intensive processes like the Bayer and Holt-Héroult methods. It has very high energy use and emissions, mainly from electricity during the smelting process. The material requires extensive transport from mine to refinery to smelter and finally the worksite, but is highly recyclable with much lower energy needed when reused, which in the long run offsets some of the initial transport cost. Production causes serve habitat loss and environmental damage, causing huge amounts of energy use and emissions. These are offset during use as the aluminium improves energy efficiency by reducing heat gains. Although the initial upfront cost may be higher, its durability and low maintenance makes up for it. Social impacts include mining and production, which can negatively impact workers and communities. Overall, aluminium is effective in use, but its sustainability depends on reducing production impacts and increasing recycling.
This section explores sustainable material alternatives and ways to improve overall performance of the John Nyland Scientia building. We focus on both structural and non-structural materials, showing how smarter material choices can significantly enhance long-term performance and sustainability outcomes. From our life cycle sustainability assessment, precast concrete was identified as a major source of embodied carbon due to cement production. Geopolymer concrete replaces cement with industrial byproducts such as fly ash and slag, making it a low-carbon alternative. Geopolymer reduces emissions by up to 90% while maintaining similar strength and durability. Geopolymer has higher costs and more complex manufacturing requirements. Fiber cement panels offer a lower impact alternative to aluminium cladding. Fiber cement has lower embodied energy, lower emissions, and reduced water and energy usage. Benefits of fiber cement panels are that they are durable, fire-resistant, and more suitable for Sydney's climate. However, fiber cement panels lack the translucency and design qualities of aluminium panels. Improving existing materials through recycling and cleaner production methods can significantly reduce environmental impact and increase overall sustainable production.
In conclusion, while the key materials used in the Scientia building provide strong performance, they also create environmental challenges. Precast concrete contributes to high embodied carbon, and aluminium panels require energy-intensive production. However, alternatives such as geopolymer concrete and fiber cement panels can significantly reduce environmental impact while maintaining performance. Overall, this shows how informed material selection can improve sustainability while still preserving the building's design and function. To complete this project effectively, we established a WhatsApp group early on to maintain clear and consistent communication. We divided the work into 4 equal sections, with each member assigned a specific role and responsibility. We also set internal expectations and deadlines, with regular check-ins to track progress. Having a group leader helped coordinate tasks and ensure the final report and presentation were consistent and well structured. A key learning from this project was the importance of clear communication and early planning to manage time effectively. We also developed our ability to work within strict word limits while still maintaining depth of analysis. Additionally, we improved our research skills by focusing on credible sources and ensured our work aligned closely with the marking criteria. Overall, strong collaboration contributed to a more cohesive and high-quality final outcome.